The moment we've all been waiting for has finally come. Hooray! We get to talk about entropy. This is probably the main reason why I wanted to have a thermodynamics unit, because entropy is one of the coolest things ever. Maybe the coolest thing ever. We'll debate that, I guess. You've probably heard of entropy at one point or another. I know in chemistry you actually calculate entropy, but I want you to understand really deeply what this entropy stuff is and why it's so important to your life and to the evolution of the universe as a whole and all of science. So the definition that you've probably heard is that it's a measure of disorder, which is a decent definition. You'll notice I put it's approximately a measure of disorder. The reason why I say that is disorder is kind of a subjective term, right? What is orderly and what is disorderly is kind of in the eye of the beholder. For example, if you've got a glass of water versus a glass of ice water, which one is more orderly and which one is less orderly? Well, I mean, the ice water, it's got some chunks in there, and the regular water looks like it's nice and smooth and orderly, but it turns out that the water actually has higher entropy, which means it has less order than the ice water does. The other thing that influences it is the size of your system. So if you take, say, like the Statue of David, it's a pretty good size hunk of marble, and if you compare the entropy in that to a little marble rock that's just jagged and has no particular form to it, the entropy of the Statue of David is actually higher because there's just so much more material there. So more accurately, and we'll get into these details more later, but just to give you a taste, what entropy is really telling us is the number of ways that we can rearrange a given system and not be able to notice that we rearranged anything. So for instance, if you have all of the particles in the room you're sitting in, the particles of air, you could swap a particle above your head for one that's behind your back, and you won't notice that the room is any different. So there's a whole bunch of swaps you can make like that, and so we would say that the gas in the room has a really high entropy. If you have just a real tiny container of gas, then you have fewer swaps, so there's less entropy there. Or if it's in a really ordered system, you can't change things. You know, if you have a painting, you can't grab one corner of the painting and swap it with the other corner of the painting and not notice. So that would be a lower entropy system. It has more order to it. Now, right along with entropy is the law that describes entropy. This is the second law of thermodynamics. And it can be stated in a whole bunch of ways. I'm going to go over in class some other definitions of or other statements regarding the second law of thermodynamics, but probably the most common one is that entropy tends to increase. And this is a nice word right here. Usually with our laws of science, we don't have tends to in there. We say it does this, energy is conserved, it doesn't tend to be conserved. And this has to do with the statistical nature of the second law of thermodynamics, again, that we'll get more into later. But this is a pretty good law. You can, in most situations, you can count on it increasing with a very high probability. The second law is actually the best explanation for why we can't harvest all of the thermal energy. When we talked about heat engines, there has to be waste heat. And essentially, any process has to increase in entropy, and that increase is always degrading usable energy into unusable energy. That's another way to describe what entropy is. It's the amount of unusable energy that there is, and it's always increasing over time. And in fact, this is one of the coolest aspects of the second law of thermodynamics, is that it gives us what physicists call an arrow of time, meaning time goes this way and not the other way. There is only one future and one past, and you always go from the past to the future, never the other way around. So let's look at that idea a little bit more. Here's our nice little arrow of time. all of the fundamental laws of physics, aside from the second law, conservation of energy and whatnot, they are completely symmetric. And by that I mean, if you do some calculation, you know some information about a given situation, you can calculate what the next situation is going to be at the next moment in time. So position, velocity, acceleration of an object, you know where it's going to go in the next second, but you can also calculate where it came from. If you think about maybe a baseball flying in a nice parabolic trajectory, if you had a film of that, and if you didn't have any other objects like the player hitting the ball, you couldn't. All you saw was the ball in the air. You couldn't tell which way the film was playing, whether the ball going this way was forward in time or the ball going that way and forward in time was forward in time. Either way, it's going to follow a parabolic arc and follow all of our laws of projectile motion. And energy and momentum will not tell you which way it has to go. We can put in negative signs for all of our times in all of our equations, and those equations will work just fine, and they will tell us where the thing came from instead of where it's going. So that is really the only reason, the second law is the only reason that the future is distinct from the past. And that's kind of an important thing. That's a rather large aspect to our lives, and it's all thanks to this wonderful, little, confusing, crazy, mind-boggling second law. Let's look at a couple other things along those lines. So here we've got a magical video here. I didn't give you the full video, just a few snapshots, but we've got a broken mug that spontaneously jumps up off the floor, reassembles itself, and lands nicely on the counter. Well, as far as conservation of energy is concerned, that is a completely possible scenario. Where does the energy come from? Well, thermal energy. This cup could absorb energy from the tile, from the air around it. Conservation of energy has no problem whatsoever with thermal energy becoming kinetic energy and gravitational energy as this cup flies up. As long as the total amount of final energy equals the initial energy, the thermal energy it absorbed, no problem. Energy has no problem with that. Now the second law, on the other hand, it allows us to calculate the probability of these types of events. And it basically says that it's impossible, not completely impossible. It doesn't prohibit it. It actually says that there is a small chance that this can happen. All you have to do is wait for, like, I don't know, 30 billion years or something like that, and then the probability would be slightly above zero. So if you've got nothing to do, go ahead and watch for these types of events. So really, it's the second law that allows us to make sense of time flowing in our world. We kind of intuitively think about the order in which things happen. If we see this broken mug, we intuitively think, in the past it was a complete mug, in the future it will never be a complete mug again. We say that this doesn't happen. What is shown in these pictures here doesn't happen. If it weren't for the second law, then we wouldn't think that way. We would see this broken mug, and chances are this came from some pile of ceramic dust, not from some even lower entropy, more organized state, because that would be even less probable than having the mug in this state. And we'll get into those details more. I keep saying that, sorry, but that's the truth. Okay, a couple other things. You might be thinking, well, if entropy is always increasing, or at least it has an astronomical probability of always increasing, what about when I clean my room and I pick up all those clothes and put them in the hamper and I wash them or whatever, and I organize my papers on my desk? Have not I created a more orderly state and broken the second law of thermodynamics? Well, sorry, you're not that powerful. If you have a single part of a system that you're looking at, entropy can decrease. But if you look at the overall process that it took to do that, namely you cleaning your room, the overall entropy of the entire system will always increase in every single case. We have never seen a violation of that. So for the cleaning your room example, you are going to metabolize some food, and you are going to give off some heat, and that's thermal energy, and you'll heat up the room a little bit, and all of those things will go to increasing the entropy by a greater amount then you decrease the entropy by organizing your papers and your clothes and whatever else. In fact, there's a long story about trying to figure out if this could ever be violated. There's a cool little thought experiment called Maxwell's demon. This is named after James Clerk Maxwell, who gave us our equations for electricity and magnetism. And he thought, well, what if I have a box of gas where it's in equilibrium, so the whole gas is pretty uniform temperature, and then I put some separation between two sides of the box. And you can imagine doing this with some mechanical means, I guess, as well, but he thought about having a little sentient entity in there that came to be known as Maxwell's demon. And let's say he's got this little trap door in the wall that he can open and close. So if this is a gas, you've got these different particles in here whizzing about, and both sides were at the same temperature initially. And remember, temperature is a measure of the average kinetic energy, or the average speed, what we called the RMS speed. But that doesn't mean that they're all exactly at that speed, all the gas particles. Some of them are traveling a little bit faster than that, and some are traveling a little bit slower. So let's say that this guy, Maxwell's demon here, whenever he sees one that's a bit above average on the left-hand side, he lets it through the door. And if it's below average, he keeps it over here. And then he does the opposite thing on this side. These ones, above average, he keeps the door closed. But if it's below average speed, then he lets it through. Well, eventually you'd have the lower average particles over here, so you would have the temperature go down on this side, and you would have the temperature go up on this side. And the idea is that there was no heat pump put in doing this, so you would kind of, in a way, spontaneously separate hot and cold particles. And the thought experiment is, could there be a device that could possibly do this and thus violate the law of second law of thermodynamics just by being able to see what's going on the microscopic scale? Well, it turns out that any process doing this, even if it's this sentient being thing just measuring or thinking about the speeds of these particles, that's going to produce more entropy than the entropy would be reduced by doing this. Another way to say what's going on here is it was less ordered, and now you have it separated, so you've sorted it and you've increased the order. But in order to do that, just the thought process alone is going to produce enough entropy to cancel out the entropy decrease of the box. So anyway, it's kind of a famous little thought experiment. If you got some time, go look up Maxwell's demon. Quantifying entropy, because up until this point I've just kind of talked about it qualitatively. We do have equations for entropy. This is the one we're going to use in our calculations. We're going to say the change in entropy of a system is equal to the heat flow divided by the temperature of the system. Here is the more robust definition. This is the real definition. The other one is just kind of an approximation that works pretty well. This has to do with what I mentioned earlier, counting the ways you can rearrange a system without noticing that you rearranged it. This K here is Boltzmann's constant, the same one that we have used before. B-O-L-T-Z-M-A-N-N. Boltzmann's constant. This omega here is what we call the multiplicity. Which is the number of ways of rearranging without noticing. So if you take the natural log of that, multiply by Boltzmann's constant, you get the entropy of a system. And the units are going to be joules per Kelvin. This multiplicity is unitless, and Boltzmann's constant is also measured in joules per Kelvin. So both of these give you entropy in joules per Kelvin. Alright, I'll show you a few calculations, and then in class we'll hopefully have some lively discussions on how your life is shaped by the second law of thermodynamics. See you next time.